Okay, well, we have this equation for the mechanical system, this equation for the LC circuit. Okay, this for a simple harmonic oscillator, this for an LC circuit. We solve this equation, we just let x equal c e to the RT, plug it in, and solve for r. Then we use that solution, plug it in here, and see what we've got. That's very straightforward, and I haven't gone through the details here because everybody's familiar with them, but x double prime is going to be what? C r squared e to the RT. And x is just going to be c e to the RT. So if we plug in for x double prime and x, we'll be able to divide out the c e to the RT. It appears both in the x double prime and the x. And the only difference between the x double prime and the x is going to be that the x double prime has an r squared that comes from the chain rule. So we're going to get the equation mr squared plus k equals 0. So that, well, we solve that equation very easily. R squared is going to equal negative k over m. So r is going to be square root of k over m times I being the square root of negative 1. It follows then, plugging this back in here, that x is c e to the omega I t, where we use omega to stand for the square root of k over m. And there's an interpretation of this that everybody at this point should be very familiar with. It's just the angular frequency of your oscillator. And this invokes the unit circle model, which we get to up here. So, of course, then using Euler's identity, e to the omega I t is cosine of omega t plus I sine of omega t. Let's dot that I to make sure everybody reads it as an I. Then either the real or imaginary part of this solution is itself a solution to our equation. Now, or any combination thereof, it turns out, because C can be any complex number. We're into complex numbers here. Let C be any complex number. So whatever combination of a cosine and a sine, if we want 7 cosine plus 3 sine, okay, we could let C equal 3 minus 7i. And we would get a real part that's equal to 3 cosine plus 7 times the sine of omega t in both cases. So it's very easy to do that. Now I'm glossing over that because what it comes down to then is your general solution could be any c1 cosine omega t plus c2 sine omega t. Just let your complex number c be little c1 plus minus little I c2, and the real part of this solution is going to be just this, right? Okay, or if we want the imaginary part to equal that, well, you can figure out what it would be. And we know from basic high school trigonometry, the sum of two angles formulas for the sine and the cosine, that C1 and C2 can be used with those identities to get the value of A and a value of phi, so that you have a solution x equals A cosine of quantity omega t plus phi. Also, incidentally, from this, it follows that your velocity function, being the time derivative of your position function, would just be negative omega times A sine of omega t plus phi. But right there's everything you need to know is right here. If you want the acceleration, we'll just take the derivative of that. You get negative omega squared times the cosine of omega t plus phi. Very simple. Okay, well, how does that compare with our solution of this equation? Well, I used C for my constant here. Might not have been the best choice because I can't use C over here because I've got a C for my capacitance. Now I've got a fancy C with a little bar through it to indicate that it's capacitance and not just the plain old letter C, but we still don't want to let Q equal C e to the RT, so we let it equal D e to the RT. I don't want to use A because A is going to down here stand for amplitude, and we want an A down here, so we don't want an A here, although we often use an A. So we plug this in, and same thing happens. Our second derivative is going to have an r squared times what this, and our q function doesn't have the r squared. So that when we plug this in, we can divide by the dE to the RT, and we're going to be left with an r squared here, so we have LR squared. We're going to be left with just plain old 1 over capacitance here. Okay? And we solve for R, and we get 1 over the square root of LC times I. So now we have Q equals dE to the omega IT, with omega equal 1 over the square root of LC. So we have Q equals D times the cosine of omega t plus I sine of omega t. And in general, that's going to be some C1 cosine omega t plus some C2 omega t. It doesn't necessarily have to be that, but we can take this thing and make it into this. At least make the real part into this, and the imaginary part we simply discard. Okay, well then that can be in the same way put into the form A cosine of omega t plus phi. And right now your Q function looks exactly like your X function. Now your constant A that you're going to get by applying initial conditions in this case is going to be a charge, and your constant A here is going to be a position, or it's going to be a length. It's going to be in units of meters if you use SI units, where A would be in coulombs if you're going to use SI units. And then, of course, we can take the derivative of this and get the current. Okay? Well, we'll talk a minute about the circular model and look at the other equations that are solved in a completely analogous way. The equations we have for a circle that does have a circuit that does have an inductance, a capacitance, and a resistance. And then one that just has an inductance and a resistance, and one that just has a resistance and a capacitance. Now we've already seen a lot of these. Just those are the equations we get, and they can all be solved in the same way. Okay, well, let's just talk a minute about the unit circle and what that tells us, because that's going to be very important. That's going to lead us to the idea of the phasors and reactants and so forth. So we have to take a look at it.